I guess you are able to see my screen, right?
Yes.
I guess you are able to see my screen. Yeah.
Yes.
Yes, sir.
Yes, sir.
Okay. So we start with a new topic, that is the systems of equations, first order equations. So system of first order equation means that there are two equations or maybe three equations, or it can be a number of equations. Okay, so we have xt, okay, so which is x1t, x2t, like this, xnt, and its transpose is a vector of n functions. Okay, so xt is x is actually a vector valued function from an interval contained in R to Rn. And we have to find such a function satisfying the system of equations which are like this. So x1 prime, which is equals to f1 of t, x1, x2, xn, and x2 prime. See that the right hand side is a function of t, x1 and x2 also, x2 up to xn. Okay, so similarly you have the x2 prime is f2 of t. Again it depends on x1 also, x2 also, and up to xn. So it is going to be xn prime is going to be fn of t, x1, xn. So each of these functions, there is a differential equation satisfied by the function x1, but the right hand side is not just x1, so you cannot integrate only this equation. This equation you cannot integrate. So integrating this equation requires also x2, but x2 also satisfies another equation. Okay, so like that. So this is such kind of a thing is called the system of first order differential equations. So the initial value problem will have the this equation. So we can write this equation in the short form like this. So f is a vector, x is a vector of t, x. Okay, with the x bar at a point t naught is going to be x naught in the vector form. Right? Everything is a vector here. So that is how we denote the initial value problem like this. So how do we talk about what is the meaning of existence, uniqueness, and how to prove these kind of things for this kind of systems of equations? And so we need to understand first the linear system, okay, and then let us try to look at some things about the nonlinear systems, like existence, uniqueness, what we studied in case of one equation. So for the initial value problem, we can talk about the existence and uniqueness. Okay. So if you look at the way we had the real analytic functions, you can do the same thing here also for real analytic functions. Okay, so you have the initial value here, and therefore you have the x prime here. You can differentiate this equation to get x double prime and use the initial condition at the t naught. So you can keep finding all derivatives, and therefore you can write the so-called the Taylor series for each x1, x2, xn. Okay, for each x1, x2, xn, using the values of x2 prime, x3 prime. Okay. So that is the Taylor series solutions we can write and formally, and one can also check it by if this f1, f2, fn are all real analytic in this in their variables. Okay, so these are n variable functions now. So in n variables you can talk about the real analytic functions. Okay, like double series you can write n series. So all these things can be generalized to 2 variables, 3 variables, 4 variables, like the Taylor series. So one can write the series and then majorize that series by the same kind of concepts that we had for one function. This time it is going to have n functions, but those concepts can be done. Therefore, the existence of real analytic solutions and the Cauchy-Kovalevsky theorem will be the same. It can be done for this kind of system of equations, provided this f1, f2, fn are real analytic functions. All those general definitions that we had about the real analytic functions, like the power series in n variables, all those things one can write. Okay, so the next question is about the Picards. So how do one talk about Picards? Because this is more general than real analytic solutions. So let us look at what is the way to talk about existence and uniqueness for ellipsis functions. So for that we need to define what is ellipsis function here. Okay. So we call, let me introduce some notation here. So this x is now a vector. Okay, so x is now a vector. So it is actually from an interval to Rn. So therefore, we can talk about norm of x. Okay, so this is going to be the x1 square plus x2 square plus xn square and power half. So this is basically the mod of a vector. Okay, but it's only that there are functions now. It depends on t. It depends on the variable t. So for a vector, we can define this. This is called the norm, or you can write it as a mod also. You can also denote it with mod x. That's also fine. So a function like a vector valued function, say f t x bar, is Lipschitz. Okay, around the in a rectangle. This is not going to be a rectangle like what we see in 2 dimensions. It is now a more generalized rectangle around the point t0 x0. Okay, around the point t0 x0, if there exists a constant L such that the norm of f t x minus f t y is going to be less than or equals to L into norm x minus y. Okay, for all x in R. You can write t comma x and t comma y. Okay, so this is the way one can define the Lipschitz continuity. So Lipschitz functions. The function is called Lipschitz if it satisfies something like this. Instead of the mod, here we have a norm. It's just the mod of a vector. Mod of a vector. So one can write the way what we wrote earlier. Just integrate the equation. Each of these equations we can integrate. Each of these equations we can write the associated integral equation. Okay. So we can write that integral equation as x1 is equals to, so you have the x0 1, you can write like this, plus the integral t0 to t f of f1 of t s xs to ds. Okay, so like this. So you can write like this: xj is equals to x0 j plus t0 t fg of s x s. So in short, you can, in the vector form, you can write x. Okay, so this is equals to x naught plus. It's only the matter of notation. It's a matter of notation. So this is called now system of integral equations. These are called the system of integral equations. System of integral equations. System of integral equations. So a solution of this one can write by writing the Picard iterations. Okay, so the successive approximations one can write. Successive approximations. Okay, so how does one write the successive approximations? X n plus 1 vector is going to be x naught plus t naught t f of s xn ts, starting with x naught, okay, t is going to be x naught. Okay, so this starts with n equals to 0, 1, 2 like this. Then you write actually the series, the sequence xn, and then one has to talk about the convergence of the uniform convergence of the sequence. So uniform convergence of, okay, so uniform convergence of the sequence. So how does one talk about the uniform convergence of the sequence? This is xnt minus x2 supremum over t. So that is the metric. So which is normally, you can write this as denote with xn minus x. Okay, so these are all vectors like this. So the set of continuous functions with respect to this is going to be a complete metric space. Okay, and therefore we can use the fixed point theorems, okay, to show the existence and uniqueness. So this is how the theory goes here. Just that what you notice here is that whatever the earlier the integral equation that we had, we are only putting a vector form of this. So we just have to understand that each thing here is a vector. That's all. And then we have nicely introduced that the norm of a vector, and then you can write the distance, the metric here. This is nothing but the d of xn comma x, and therefore you take now the set of continuous functions, vectors now, vector valued functions. Okay. Now using that one can write the same thing about Scholar's law theorem, all those things you can write, and therefore you can even talk about the Cauchy-Peano theorems, right? So the existence, uniqueness, and existence theorems will follow. Existence and uniqueness, and Cauchy-Peano's theorem will follow. Actually, these things will follow. So that is about the existence and uniqueness and the Picard's theorems. So what is now what is important now is first of all we need to study the nonlinear systems. First we need to understand the linear system. This is what we do in the case of equations also, single equations, that before we studied the solutions of nonlinear equation like this, first we studied the linear equations. So similarly here we aim to study the linear equations, linear system of ODEs. Okay, so that is you want to consider the x prime equals to a into x, where what does this mean? So it means that you are in the form of the matrix now. So you have the x1, x2, xn, and x prime is going to be Now you have a matrix A11, A12, A13, A1n, A21, A22, and AN1, ANN, and this is X1, Xn. So in short, it is represented with X prime equals to Ax. A is a n by n matrix. A is n by n matrix. We assume that the coefficients A, J, T, they are all continuous functions. They are all continuous functions. So it is a linear system because if X is X and Y are solutions, X plus constant times Y is also a solution. That is why they are called the linear systems. So you would have studied some of you, about the number of linearly independent solutions for this type of systems. Let me do it in detail, okay, and also tell about some connections that it has with our linear algebra and Jordan canonical forms, which will be useful for us to study something about asymptotic behaviors and stability. So that's why I want to do this in details. Okay, so for studying the number of the maximum number of linearly independent solutions for a second order equation, we introduce the concept called the Wronskian. Okay, so what is the Wronskian? Wronskian for we have functions, right? So we had two functions. If X and Y are two functions, okay, X and Y are two functions, we define the Wronskian of xy, okay, as xt, yt, and x prime t, y prime t. And so recall the second order system, second order equation, linear ODE. Okay, so there we showed that there it was shown that the second order linear ODE,
linearly independent.
Yeah, so has at most two linear solutions. Also, we find that actually there are two linearly independent solutions, so that's why we say has. Okay. Therefore, the dimension of the solution space is going to be 2. So that means once, so what is the whole idea of this is that then you have actually the general solution. The concept of this is that it helps us to find what is the general solution. Say any solution of a second order equation can be written as C1 x1 plus C2 x2. There are two linearly independent solutions. We know all other solutions. That was the idea. So can we do the same thing in case of linear system of equations? That is, if you have an n by n system of equations, can we say that these are the only solutions? Say, if not 2, if there are 3, or maybe n, or a 2n, or n plus 1. But I know that these are the only solutions in the sense of linearly independence. Okay. So we know that from our linear algebra, we can talk about the linear independence even for vectors. Need not be for functions, we can even talk about the vectors. But we need those vectors to be in the form of, there should not be ambiguity when we go for differential equations to linear algebra, right? So we will try to connect that Wronskian, what we have here, in case of second order equations with the vector valued functions. Of course, for the vector valued functions, you have, say, x1, x2. If there are vectors, of course, they are functions also, xn. If they are vectors, we can top them up. They are linearly independent. If we write c1 x1 plus cn xn, equals to 0, right? Implies C1, right? Cn
For
is,
all Ci equals to 0.
yeah, all Cn's are 0. So that's how we write the linearly independent. Now let's see that we can. This is in some sense compatible with what we are writing linearly independent for the functions. Okay, so look at now this system of now look at the second order equation. Okay. So the second order equation, what we have, the second order equation. So why this vector form of writing this is compatible with the Wronskian? So look at x double prime plus a1 x prime plus a2x. Okay. So we can convert this into a system of equations. This we can convert into system of first order equations. How do we convert? Define x1 as x. Okay, and if I define this, then it becomes x1 prime equals to x prime. Okay, therefore you write x prime as x2. Okay, x2 equals to x prime. Then you have x prime is going to be x2. Okay, so this is one equation. x1 prime equals to x2. Now x double prime. Okay, so from the equation it is given to be minus a1 x prime minus a2x. So in this transformation, what we, in the new notation, x prime is going to be x2. So this is going to be minus a2 x2 minus a2. X is nothing but x1. Okay, and what is x double prime? X double prime is nothing but x2 prime. So this is x2 prime. So you have another equation here. So writing these two equations together, we have, right? So we have the following system, that is x1 prime and x2 prime is going to be the system x1 x2. Okay, so what is x1 prime? X1 prime equals to x2. Therefore this is 0 1, and x2 prime is going to be minus a2 x1. So this is minus a2 and this is, sorry, a1 minus a2 x1 minus x2. So this is again in the form of a system. The x prime equals to a2x. Okay, so this equation, the second order equation that we have here, can be converted into a system of equations like this. And if I write the Wronskian here for this system, for this kind of a system, or if you, whatever the Wronskian that we have earlier here, this one. Okay, so just see what is that Wronskian turns out to be in this case. Okay, so what will be the Wronskian? The Wronskian is going to be, we had x, y. These are the two functions, right? X prime, y prime. So in the notation that what we introduced, it is going to be x is going to be x1 and y is going to be y1. X prime is going to be x2 and y prime is going to be y2. Okay, so this is in the form of the determinant of the vectors. Determinant of the vectors. See, where these are columns. So both the notations that what we are writing here, that is, if you have a vectors x1, x2, xn, and they are going to be compatible. Therefore, we can introduce what is called the Wronskian here. Okay, so the Wronskian of the vectors x1, x2, xn. Not only the functions, we can write the Wronskian of the vectors. So this is going to be the x1, x2. This is the column. So you write the determinant like this. So this is called the Wronskian of vectors. non-skin of the vectors x1, x2, xn. So we can define now what I defined here, the definition here. They are called linearly independent if I write a sequence like this, if I write a linear combination, then the C1, C2, Cn has to be 0. Okay, or you can write the linearly dependent, or you can write x1, xn, or okay, linearly dependent if there exists a constant C1, Cn, not all 0, such that x1, C1. So this is what we write for the vectors. Okay, x1, x2, xn are vectors in a vector space. Therefore, you can write the linearly dependence means that there exist constants which are not all of them are 0, so that this combination is going to be 0. So what does this mean? This means that we have x1, okay, as a column, and x2 another column. So xn, c1, c2, cn. This is equals to 0. So there are constants c1, c2, cn which are non-zero. Okay, so this means the system of equations that if I write this as a matrix A and C equals to 0, that means that the determinant of this has a non-trivial solution, right? So as an immediate consequence of this is that if they are linearly dependent, okay, means that the non-skin is going to be 0 for all t, right? So there exist constants, so therefore we have the theorem here, which is just comes from the linear system of equations. Okay. So x1, x2, xn are linearly dependent, then implies the non-skin is, they're all vectors, 0 for all, 0 for all. So the question is that, as we know, in case of 2 by 2, in case of higher order equations also, we ask for the converse. What about converse? Okay, so the converse is in general not true, but if x1, x2, xn are solutions of linear system of equations, then converse should be true. That is what we prove in case of second order equations. So the same thing is going to be true here also. So let's see. So the first thing is about the Abel's formula. So there is a nice formula which is, so all these things are true in case of second order equations. I already told you how the second order equations and first order systems are equivalent. Okay, so with that transformation, both the second order equation and second order system, or nth order equation and nth order system, n by n system, both are equivalent or both are same. You can solve one, you can solve the other one. Okay, so what is the Abel's formula? We have the x1, xn. These are these are all vector valued functions. Okay, if they satisfy, if they satisfy the system x bar equals to ax. So a here need not be a constant. They can have functions as elements. Then we have the following formula for the Wronskian. The Wronskian of them is going to be the exponential of the integral t0 to t as ds. okay, times some constant. That is how this Wronskian satisfies. So this what is the use of this is that because of the exponential, it says that Wronskian is 0 at one point implies that Wronskian is going to be 0 everywhere. Okay, either it is identically equals to 0 or it is never 0. That's the consequence. That's the important consequence of this Abel's formula. Okay, so I'll just do this for the case of n equals to 2, but other things will follow similarly. It's not a very difficult proof. So let me write the system. So x1. So let me write x1i and x2i. Okay, derivative of this is going to be a11, a12, a1, a21, a22 into x1i and x2. So this is true for I equals to 1, 2. This is true for I equals to 1, 2. That's what we are saying. x1, x2 are the solutions of the system like this. Now write the Wronskian. Wronskian is Wt. We define it as the x1, okay, x12, x21, and x2. Okay. So we differentiate this d by dt of Wt. So this is going to be x1 1 prime, okay, and x1 2 prime. You can write the expression and then check this also. x2 prime, so x21 and x22 plus x11, x12, x21 prime and x22 prime. Now we substitute the equation satisfied by x11. x11 satisfies an equation like this. It is a11 x11 plus a12 x21. Okay. Similarly, the other one is a11 x12 plus a12 x22, and this is x21 and x22, and similarly the another matrix on the determinant. If you see the first one, here there is x2 prime and therefore here also there is an x2 prime. Okay, right? And this is a11 x1 prime and this is a11 x1 x12 x22. So this is going to be a11 into w. The other one is going to be a12 into, the columns are going to be the same, therefore the determinant is going to be 0. So similarly, plus this one is going to be this one from the second determinant a22 w. That is nothing but trace of matrix A into W. Okay, this is the trace of the matrix A into W. So you have the d by dt of W equals to trace of A into W. So you write the integrate this. Therefore, if you integrate this, and you get the result that we stated. Okay. So it shows that a corollary of this, as I mentioned, if x1, x2, xn, okay, if x1, xn they are solutions of x prime equals to ax. If they are solutions of this, then the Wronskian of them is equals to 0 at a point, or you can write like this, this and this one is this, and the Wronskian of them is 0, then the Wronskian is going to be 0 if everywhere. Wronskian is going to be identically equals to 0. So that comes from, because Wronskian now satisfies that exponential function on the right hand side, therefore exponential function is 0, is never 0, therefore the constant has to be 0. If you have any questions, you should ask me in between. If you have, just don't wait till I finish the lecture. Okay, so now we are in a position to do the X and R solutions. So why I'm emphasizing this is that these statements are true only for the solutions of differential equations, not otherwise. Okay, this is true only for the solutions of differential equation, not otherwise. Okay. Then they are linearly independent. Okay. So x1, x2, xn are linearly dependent. Okay, if and only if the Wronskian equals to 0 for what. Okay, so one thing that we have seen earlier is that if they are linearly dependent, then there is non-trivial constants, therefore the Wronskian is going to be 0. So this part is already done. Okay, so it comes from the definition of linearly dependent. Okay, follows from the definition of linearly dependent. Okay, now let's do the converse. The converse is that if Wronskian equals to 0, then they are going to be linearly dependent. Right. So how the converse comes? So suppose Wronskian is 0, everywhere means that Wronskian is going to be 0 at a point. Wronskian at a point t0 equals to 0. So what does that mean? Wronskian equals to 0 at a point means, let's go back to the system. The system says that you have C1, C2, Cn, and these are x1, x2 vectors. These are vectors. This one at the point t0 has a solution, a non-trivial solution. That's what it means, right? So this is at the point t0. At the point t0 has a solution, has non-trivial solution. Okay. Has non-trivial solution C1, C2, Cn. So with this C1, C2, Cn, now let us define a new function, say z t, which is equals to C1 x1 plus C2 x2 plus Cn xn. Okay, so this system of equation, again, this z prime is going to be, because it's a linear system, it is going to be, z prime is going to be C1 into, right, x1 prime, x2 prime, xn prime, and they are all going to satisfy the ax. So this is going to be C1 ax plus C2 ax plus Cn ax. So that is nothing but a into z. And also the z at the point t0. Okay. So from this relation, gives that z at t0 is going to be 0. Z at the point t0 is going to be 0. Also, right, so z is a solution of the system and z at t0 is going to be 0. Also, zt is identically equals to 0 is a solution. So this is also a solution. This is also a solution. So that means by uniqueness, Z and 0 are the same. Therefore, by uniqueness theorem, because linear functions are going to be ellipsis continuous, okay, Zt is going to be identically equal to 0. So what is Zt? Zt is nothing but C1 x1 plus Cn xn is identically equal to 0. Okay. So this means that these are all linearly dependent. These functions are now linearly, vector valued functions are linearly dependent. So using this, we can now talk about the general solution, since we have the a very important theorem that they are linearly dependent if and only if the Wronskian is going to be 0. Okay. Okay. So the general solution. Yes.
तो वी कैन मतलब हम लिनियर अलजेब्रा का जो नॉलेज है उसका यूज करके नहीं कह सकते कि अगर मैट्रिक्स का मतलब डिटरमिनेंट 0 है देन उसका रैंक कम होगा, दैट्स व्हाई दे आर लिनियरली डिपेंडेंट why we are taking zt as a function and then differentiate it and so on.
No, linear algebra says only for the vectors, right? It has to be only vectors of constants, right? It's not for functions. We didn't study the linear algebra for functions.
सर बट जो फंक्शन मतलब वेक्टर स्पेस बनाता है ना फंक्शंस,
No,
मतलब
what we
बाउंडेड
studied
फंक्शंस
there
और
is Ax. So here we are only using Ax equals to b, right? The matrix Ax equals to b. Here I am using Ax equals to b. There is no linear algebra here. System of equations. I cannot say if the function A is dependent on functions. This doesn't give us for all, right? If A is entries of A are functions, my Ax equals to b system is only for the constants, constant matrix. It's not for the variable function matrix.
So at the point t naught.
At the point t naught. At the point t naught, it is a constant matrix. Therefore, there exist constants C1, C2, C. Right?
Okay, sir.
Sir?
So you yes.
Sir, आपने कॉलम में लिखा है for all t.
Yeah, so that's what we are showing for all t. Right? If it is true for all t, then it is going to be t. See, what do we use? Yes, I know it is true for all t, but how do I use that information? So when from the system of equations in our systems, right? If A is a function, the entries of A are functions, then we don't have that kind of a thing, right? We don't find the inverse of such kind of matrices. We don't solve such kind of systems. So if it is 0 at all points, then first assume that it is 0 at one point. So from there you collect the constants C1, C2, Cn. That's what eventually we are showing. That this C1, C2, Cn can be chosen independent of the point t. How do we know that it can be chosen independent of the point t? Wronskian equals to 0 at all points, right? So how do we know that C1, C2, Cn are independent of the point t? We don't know that, right? Okay, so the general solution is that if they are if we have n linearly independent solutions, x1, x2, xn, or linearly independent solutions of x prime equals to ax, then any other solution, any solution then all solutions of the system, right? Any other solution, or let me write exactly what I wrote. Then all solutions
Any
of,
solution.
all solutions of the system, all solutions of the system belongs to the linear span of this x1, x2, x. Okay. The linear span of this. So in other words, any other solution, or any solution, not writing any solution, z, okay, is of the form zt equals to c1 x1 cn xn. For some constant c1, c2, c. So that is called the general solution. That's called the general solution. Okay, that is called the general solution. Okay, so how do we prove this? It basically says that if you have n linearly independent solutions, and that is the complete solution space. Okay, that is the complete solution space. So let us take, let y be any other solution. Be any other solution. Any other solution or any solution. Any solution of x prime equals to x. Okay, x prime equals to ax. Okay, so what is y? Y is in the form of y1, yn. The functions y1, y2, yn. Then consider the system. Then we consider the system. System of linear equations with constant coefficients. That is x1 at the point t0 and its vector. Okay, x2 at t0 vector like this. And putting them as columns of this matrix. C1, C. This is as the y1 at t0 to yn at a point t0, some point t0, or some t0. And such a system now will have a unique solution because C1, x1, x2, xn are, these columns are linearly independent. Okay, columns are linearly independent implies there exists a unique solution. What are the unique solution? Let me call it as, say, alpha 1, alpha 2 for the system. Okay, columns are linearly independent implies that this system has a unique solution, alpha 1, alpha 2. So now let us take, like earlier, take a function z, which is a linear combination of this. So consider zt, which is now the alpha 1 x1 plus alpha 2 x2 like this. Okay. Since it is a linear combination of these vectors and each vector satisfies the matrix equation, therefore z prime is going to be a into z. Okay, that is going to be alpha 1 into ax, alpha 2 into ax, alpha n into x. So it's going to be alpha 1 plus alpha 2 alpha n into this one. Therefore, that is going to be a into z. Right? So this satisfies. Okay, satisfies this. Also, look at what is z at t0. z at t naught is going to be alpha 1, right, at the point t naught, alpha 2, alpha n xn at t naught. And what is this? This is again in the form of the matrix that we wrote. This is S1 t naught vector xn t naught vector, and we know that this is nothing but y at t naught. It's going to be y at t naught. So what we have here is z satisfies the system with z at t naught equals to y at t naught. Also, y satisfies the system because we assume that y is any other solution of the system, right? We started with y is any solution of the system. Y is any solution of the system. Therefore, now y and z satisfies the same initial value problem. Y prime equals to ay and z prime equals to az. Okay, and both of them have the same initial condition. Y at t naught equals to z at t naught. Therefore, it's the same system. There are two solutions, right? In the sense that if I subtract this, so take w equals to y minus z, then we will have the same w prime is going to be a into w with w at t naught equals to 0, and w equals to 0 is a solution. Therefore, by uniqueness, w is 0, identical equals to 0, that is y minus z. It implies yz equals to, yt equals to zt. And we know what is zt. Zt is the linear combination of the given functions x1, x2, xn. Therefore, yt belongs to the span of this. Okay, so I will stop it here. If you have any questions, you can ask me.
Sir, can you provide the whiteboard sheet? ये जो आपने लिखा है इसको.
I didn't get. What is that?
सर जो आपने नोट्स लिए हैं ना, ये वाले भी आप प्रोवाइड करा दीजिए.
I will try, but I don't know how to convert this into a PDF file. I will try to convert this, whatever I wrote here. You mean to say that?
Yes, sir.
No, this is there in the video, no? You can see the video?
सर, बट एक्चुअली क्या होता है, वीडियो शो मतलब वीडियो ना फास्ट फॉरवर्ड होता है, ना ही उसको मतलब आगे बढ़ा के देखा जा सकता है. मतलब बहुत ज़्यादा